Hello, my friends. In this video, we are going to touch on the topic transformer. And I presume every one of you have seen transformer before. Uh, First of all, the transformer has a core. And this core is normally made with a ferromagnetic material. So this is so-called iron core. And you have a winding in the primary side. And the winding here may be N1, yeah, and then you have a similar winding in the secondary side, and maybe the winding here is N2. Now, the voltage here will, and the current here will give rise a magnetic flux. And this magnetic flux is going to be circulated around the iron core. And likewise, you also have a current in the secondary and voltage at the secondary as well. So, and these are in time domain, okay? Let's make sure you don't get confused. So this is the typical scenario of a transformer in time domain. We have learned Faraday's law before. By Faraday's law, the induced EMF. Yeah, look at the primary side. Yeah, consider only the primary side. I shouldn't use the red pen. Yeah, let's consider only the primary side. VT is going to be minus N1, and then d by dt. So now, if phi is the magnetic flux given by phi m, which is the maximum magnetic flux, sine omega t. Then, according to, if we substitute the variable phi into the equation 1, then what we are going to get is t, and then n1, and then cos omega t, okay? And do not forget that you have an omega here. Then we can safely assume that is 2 pi f, and then n1, and then yeah, it shouldn't be a big deal. So from here we can say that the maximum induced voltage is going to be this term. So V max here for 1 Yeah, I will put 1 here. Yeah, because I'm not dealing with the primary. It's going to be by the way, it's too ugly. VM is enough. VM, yeah, 1, which is the maximum induced voltage, is going to be 2 pi N1, or we don't need the minus sign here. So for the primary, you can get this. Similarly, in the secondary, you can equally get 2 pi F and 2 M. So in this case, I think it's fair to assume that Vm1 divided by Vm2 is equals to N1 over N2. Yeah, let's define a parameter, say A. A is the turn ratio. Now we have got this, the ratio of the maxima is going to be the ratio of the maximum voltages in primary and secondary is going to be A. Now, if you can express the turn ratio in maximum voltage, we can equally express this into a complex value, the root mean square value. Okay, so here I would say, right, V1 and V2 are the root mean square. Yeah, because this guy, right, divided by root 2, it is the root mean square. Okay. Now we have got this, right? V1 divided by V2 is A. But now, hang on a minute. For an ideal transformer, the power in should be exactly equal to the power out. The power in the primary should be exactly the same as the power in the secondary, given that there is no power loss. So I would say this, right? For an ideal transformer, I1 V1 is equal to I2 V2. They are all in root mean square value. If root mean square value work, then the phasor will also work in the same manner. So now you have the these relations here, and you also know that V1 divided by V2 is I. So we can say this V1 I1 divided by I2 is equals to 1 over A. So this is another important relations for an ideal transformer. Now, I don't have enough space here. I'm going to erase this part, and then we continue. And now, what we have is, right, V1 divided by V2. They are root mean square is equal to A. And another thing is, right, I1 divided by I2. is equal to 1 over A. So these are the important findings we have got. And now, so far we are now assuming the transformer is ideal. And what we don't have is now you have an ideal transformer. Yeah. Let's use the schematic to represent it. You have an ideal transformer. So this is the way how we represent transformer in schematic. And then the ratio by N1, N2, N1 over N2 is always A. The current here, the voltage here is I. Yeah, I'm now using phasor, I1. Yeah, phasor is the same as root mean square, okay? And then V1. So this is the ideal transformer. And we have I2 and then V2. So if you have a current going through something, right? We don't know what it is, right? Let's say this is the Z2, the primary impedance. So in this case, we can just say the output impedance, Z2, is equal to V2 over I2. Okay? Now, what is V2? Can we express V2 in terms of V1? Yes, the answer is yes. This one is going to be, according to here, V1 divided by A. And how about here? The current. What is I2? But I2 according to here, yeah? If I2 is moved to the right side of the equation and A moved to the left side, then we can say I2 is I1 times A. So obviously, V1 divided by I1 is equals to in here, right? In this case, we get A square Z2. So in other words, if you are given a transformer like this, you don't really need to write this much. Right now, you have the relations of V1 and I2, 1. So can we log this, draw a conclusion here? This one is equivalent to V1, I1. So instead of doing all these things, we can safely say that you don't really need to go through all this analysis. So this process, instead of labeling the low impedance Z2, instead of being so inflexible, right, we can easily scale Z2 by the turn ratio square, and then we'll make it as a circuit element for the primary. In this case, you can forget about the turn ratio, this transformer symbol, I1, I2. So you can use this way, use only the parameter for the primary to calculate the rest of the circuit. So from here to here, this is the process of referral. What we did is, right, we refer Z2 to the primary side. So what we have done is referring Z2 to the primary. So this is a very powerful circuit technique for analyzing a transformer. And so far, we have only considered the ideal case. So what happened, right? If we are using a practical transformer. So now back in the beginning of the last century, some engineer has already come up with a way to resolve all these transformer problems. So they believe the real transformer is an ideal transformer. Ideal in the sense that there is no power loss. Is an ideal transformer plus loss. Plus losses. And so this is the theory. The real transformer is equivalent to an ideal transformer together with some losses. And what losses you are talking about? The losses here include the one, Kappa loss. And two, iron loss. Losses. So let me explain to you what Kappa loss means. Kappa. So what is made with copper in a transformer? Obviously, it is the winding, the copper winding that contribute to copper loss. So this means that the copper winding itself contributes to the resistance. So instead of writing a transformer here, what we can do is we can have an ideal transformer, but then do not forget that it has a copper loss. Kappa Loss. So this is R2. And if there is a Kappa Loss, then there should be a impedance for the attached to the copper wire as well. So let's say this is X2 for the impedance, right? X2 itself is J omega L2. So the inductance will cause this loss. So, and if you can get the Kappa loss in the secondary, you can easily get Kappa loss in the primary. So another conclusion that has been come up with is I'm now trying to save face. So if we can model the secondary couple winding with R2 and H2, we can easily do the same for the primary. And this one is actually L1. Likewise, if you can do that, then right, yeah, let's say this, V2, V1, now, what about iron loss? Iron loss is what? Iron loss is actually the loss caused in the core, the iron core of the transformer. You know, why in the transformer, it look like this. After operating for a while, then you will feel some warmth in the transformer. So this is the transformer. And in addition to the resistance in the copper winding, you also experience some loss here. And this loss will happen in the iron core, in the core only. And the loss will dissipate as heat. And also some eddy current. So the iron loss here contain two elements. One is the eddy current. Loss. What else? Now eddy current is one element. Another element is the magnetizing loss. So this is so-called hysteresis loss. So these two losses also contribute to the transformer performance efficiency issue. And the transformer here has already taken care of the Kappa loss. So we need to include iron loss, core loss, and the core loss is normally magnetite. Yeah, it's normally modeled as a parallel component in the transformer schematic model. And the parallel components include the RC. RC stands for the eddy current loss. And also why you have a XC, XM. XM stands for the hysteresis loss. So this is the reality of a transformer. Yeah, let me withdraw it. It's not very clear now. And again, and 1 and 2. So this is the reality of a transformer. And when we say V1, right, it should be the V1 here. So I don't, well, maybe I can just say VP, right? And then the voltage here is VL. And V2 actually refers to this voltage, the ideal voltage. And V1 is this voltage. So this is the full equivalent circuit for a practical transformer. The practical transformer has two kinds of losses. Kappa loss. Kappa loss is due to the copper resistance in the copper winding. And this loss happens to the primary and also secondary. Another loss is the core loss, the iron loss. Iron loss means the loss in the iron core, and these loss uh, are the combination of eddy current loss, which can be accounted for by RC and hysteresis loss. So this is the way how we model the transformer. Now, you may think that with a transformer like this, it's very difficult to model. But don't worry, we have learned a lot of tricks already. We can use these tricks to transfer, to model this transformer. Now, I don't have enough space here, so I'm going to erase this. And I will leave this circuit here. So before going on further, let's give a name for this schematic. This is the so-called full circuit, yeah, full transformer circuit, yeah. Now your job is to analyze the circuit, and one thing you can do is use this technique. We can refer Z2 at the low to the primary. We can easily refer any element on the secondary back to the primary. So in this case, you have R2, X2, and BL. So why don't we refer it to the primary? So instead of drawing a circuit like this, which is very complicated because of the presence of this transformer sign here, we can eliminate this transformer sign. So we continue, right? The primary is not going to change. And X1. And now you also have a core. The core is like this. So this is the primary circuitry. And instead of including the transformer side here, we use the technique we have learned. And now you have a voltage here and the current here. So we exclude the transformer. Instead, we refer everything, every parasitic elements to the primary. So we have R2 here. Then if we refer it to the primary, then we have to make use of what we have learned here. For every impedance, we will scale it up by A squared. So by the same tokens, we have A. So this is the way how we refer the circuit element here. And how about X2? Yeah, you can do the same thing. A squared X2. And if there is any law here, presumably, right? This is the ZL, right? ZL, right? We don't know what kind of impedance here. Yeah, ZL. And then the ZL will be equally converted to the primary. L. Now, if the voltage here is VL, then we also need to convert it to the primary side. Like what we have here, right? For every Z2, right, A P1 has to be divided by times A. Yeah. So the voltage here is not VL, instead AVL. So this is the way how we come up with the equivalent circuits. And this equivalent circuit doesn't include any approximation. And that's why we call this equivalent circuit flow equivalent circuit. And this is enough for you to analyze the transformer with the simulator, MATLAB, everything, right? You can derive the formula for the input voltage according to this circuit. And you can also work out the voltage regulation. And obviously, you can also calculate the efficiency. But this circuit is somewhat complicated. In the old days, when the engineer doesn't even have a calculator, so they try to approximate everything in a way that they can handle it with manual calculation. So what they did is, now that's okay, we have this circuit, but the core loss here is very ambiguous, right? If we can do that, right, it's just a parallel element. Why can't we move this core to here? Because this is a high impedance element. We can just move it to there. Then we end up with a so-called approximated equivalent circuit. By the way, right, I presume everyone of you don't need to erase it. So what we can do is, right, we move it to the entry of the primary. So without any change, you have a primary like this. But now this time, the this Kappa Loss and the series one are going to combine with each other. And this guy here will be the sum of these two impedances. And this guy here is x1 plus a squared x2. And again, right, the voltage here is not going to change. A squared z2. Yeah, by the way, I make a mistake here. It shouldn't be ZL, it should be A squared ZL, okay? So we end up with a much simpler circuit. And in the next video, I will teach you how to obtain those um, copper loss and iron loss by experiment. And for the time being, I think we have already got enough information for us to move forward. And before the closure of this video, I'm going to give a name for this circuit. You have two equivalent circuits here, and this one is what approximate the equivalent circuit. So basically, we have everything. If you have any questions, please leave your questions to the comment box underneath the video. Thank you very, very much for your support.